Try thinking about this seriously. In the Milky Way galaxy, with roughly 100 to 400 billion stars, it is almost certain that there must be countless Earth-like planets. And by that logic, life, even intelligent life, should not be rare. So the real question is not, is anyone out there, but why we have never seen them, never received any clear signals, and never had anyone come here. That is exactly the question Enrico Fermi posed in 1950 at Los Alamos, when he simply asked, where is everybody? This led to what is now known as the Fermi paradox, a very uncomfortable contradiction between probability and reality. And there is one possibility that few people want to face. Perhaps civilizations not disappear or fall silent, but they simply cannot go any farther, because travel between the stars is tightly locked by the laws of physics that no one can overcome. And if that is true, then to understand the silence of the universe, we must begin with the most fundamental limits of nature itself. So let's start with the first barrier, and also the most important one, the speed of light. In modern physics, the speed of light in a vacuum is approximately 299,792 kilometers per second. And what matters is not how fast it is, but that nothing in the universe can exceed it. This limit is not an assumption. It comes from the theory of relativity published by Albert Einstein in 1905, in which space and time are linked together in a way that makes the speed of light an absolute constant. When an object begins to approach that speed, everything changes. Its effective mass increases, and the energy required to accelerate it further does not just rise, it approaches infinity. That means you can get very close, but you can never actually reach it. To see this more clearly, look at the fastest spacecraft we have ever built, the Parker Solar Probe, which reaches speeds of about 700,000 kilometers per hour. That sounds very fast, but in reality it is only about 0.064% of the speed of light, a number that is almost insignificant when talking about interstellar travel. And even if you imagine a ship that could somehow reach the speed of light, the journey to the nearest star system, Alpha Centauri, which is about 4.37 light years away, would still take more than 4 years under the most ideal conditions. But in reality, any ship we could actually build would be much slower than that, turning the trip into tens of thousands of years, far beyond any time scale that humans could experience or sustain. So the problem here is not that we need a faster engine, but that we are facing a limit that no technology can break. And that means the distances between the stars cannot be solved simply by increasing speed. And if you think the speed of light limit is already the biggest obstacle, the next barrier is far more unpleasant. Because even if you accept that you cannot exceed that limit and only try to get close to it, you immediately run into a more fundamental problem: energy. In physics, the energy required to accelerate an object to relativistic speeds is described by the famous mass-energy equivalence equation proposed by Albert Einstein. What matters here is that energy does not increase linearly with velocity. It increases extremely rapidly as you approach the speed of light. That means every additional percentage of speed you want to reach costs vastly more than the previous percentage, in an almost uncontrollable way. Try to imagine a ship with a mass of about 1,000 tons, not too large compared to modern engineering projects, and you want to accelerate it to just 10% of the speed of light, or about 30,000 kilometers per second. You would need an amount of energy on the order of 6 times 1020 joules, which is roughly equal to nearly all the energy that human civilization produces in an entire year. To make it more concrete, global energy production is about 580 exajoules. That means that just to accelerate a single ship to a small fraction of the speed of light, you would already need nearly the entire energy output of the whole planet. And that does not even include the energy you would need to carry to decelerate when you arrive. Without it, you would simply fly past your target at enormous speed and be unable to stop. And if you think we could simply build a larger ship with more fuel, the problem immediately returns, because that fuel has mass, and that mass also has to be accelerated, which requires even more energy. This creates a vicious cycle in which every solution makes the problem worse. Now look at what we actually have. Chemical rockets like NASA's Saturn V, which took humans to the moon in 1969, work by burning fuel to create thrust, but their energy conversion efficiency is extremely low compared to what is needed for interstellar travel. Even modern improvements like ion engines, while more efficient, are still far too slow to solve this problem in any reasonable time frame. You might think of nuclear energy, which is far more powerful than chemical fuel. But even that is not enough to close the enormous gap between our current capabilities and the requirements of an interstellar journey. One of the most attractive ideas is to use antimatter, because when matter and antimatter meet, they convert nearly all of their mass into energy, making it the most efficient energy source we know. But the problem is that we can currently produce only tiny amounts of antimatter in particle accelerators. And the cost to produce just 1 gram can reach billions of dollars. Not to mention that storing it requires extremely stable magnetic systems, where any mistake could lead to instant destruction. And even if you somehow solved all those problems, you would still face the reality that energy is not something you can create infinitely, because the conservation laws of physics do not allow it. This turns the energy problem into a real limit, rather than just a technical challenge. And when you combine it with the speed of light limit we discussed earlier, you begin to see a clearer picture. It is not that we are not smart enough to reach the stars, but that the universe may be built in a way that makes it almost impossible. Even if you assume that somehow we solved the energy problem, you are still not out of trouble. Because once you start moving at speeds high enough to travel between the stars, you will face a danger that most people never think about: collision. There is a very common misconception that space is completely empty and you can fly through it without encountering anything. But that is not the case. The space between the stars, what we call the interstellar medium, still contains gas and dust particles with an average density of about 1 atom per cubic centimeter. That number sounds so small it seems negligible, but when you stretch it across distances of many light years, you realize you are traveling through an environment that actually contains matter. At low speeds, this is not a problem. But when you begin to approach a significant fraction of the speed of light, everything changes completely, because kinetic energy depends on velocity in a way that makes even tiny objects extremely dangerous. Imagine you are traveling at just 10% of the speed of light, about 30,000 kilometers per second, and you hit a dust particle only a few micrometers in size, much smaller than a grain of sand. At that velocity, the energy carried by that particle could be equivalent to a bullet fired from a rifle. That means every small collision feels like you are being continuously shot at the hull of your ship. Now multiply that by billions of times over a journey spanning many light years, and you begin to see that the problem is no longer a rare accident, but a continuous process of erosion. There is no way to completely avoid these particles, because you cannot detect and dodge every single atom or dust grain at those speeds. And even if you could detect them, you would have no time to react. This turns space from a quiet void into an environment like an invisible storm, where you are constantly being bombarded by extremely small objects carrying enormous energy. You might think the solution is to build a shield thick enough to protect the ship, but you immediately run back into the problem of energy and mass. The thicker the shield, the heavier the ship. The heavier the ship, the more energy is required to accelerate it. And we have already seen that vicious cycle. And the problem gets even worse when you consider that not all particles in space are small. There are still larger dust fragments and even micrometeoroids. A collision with such an object at relativistic speeds would no longer feel like a bullet, but like a small explosion occurring directly on the ship's hull. No material we know today, whether steel, titanium, or the most advanced alloys, could withstand such continuous bombardment over long periods, especially when each impact occurs at extremely high energy levels. Even if you imagine stronger future materials, you still cannot eliminate the problem entirely, because you do not just need to survive one impact. You need to survive billions of impacts throughout the journey. And all it takes is one sufficiently large impact in the wrong place for the entire ship to be destroyed. And if you think we could solve this by placing a sacrificial shield in front to absorb the collisions, you return to the same problem. That shield would gradually erode over time, and you would have to carry spare mass to replace it. That again increases the total mass of the ship, and the energy loop reappears. Some scientific proposals have considered using magnetic fields or plasma to deflect particles from the ship's path. But the problem is that electrically neutral particles are unaffected by magnetic fields. And at relativistic speeds, reaction time is almost zero. This means you do not just need a perfect protection system. You need a perfect system in an environment that allows no margin for error. And when you put all of this together, you begin to see a very clear picture. Interstellar space is not an easy void to cross, but a continuously dangerous region where every centimeter you travel carries risk, where every small collision can become a disaster, and where simply surviving the journey is already an almost insurmountable challenge. Suppose that somehow we manage to protect the ship from interstellar collisions. There is still another danger that is even harder to control, because it does not come from things you can see or avoid, but from the very nature of space itself: cosmic radiation. The space between the stars does not just contain dust and gas. It is also flooded with high-energy particles, protons, electron atomic nuclei, traveling at nearly the speed of light. What we call cosmic rays are essentially enormous energy bullets shooting through space in every direction. These particles can penetrate matter with astonishing ease, breaking molecular structures and causing direct damage to DNA, something we barely notice on Earth thanks to the thick atmosphere and the planet's magnetic field. But the moment you leave that protection, you begin to experience a completely different environment. Astronauts on the International Space Station, orbiting about 400 kilometers above Earth's surface, already endure radiation levels many times higher than normal people. And even though they are there for only a few months, the accumulated radiation dose is a serious issue that must be strictly monitored. Now extend that, not for a few months, but for decades, centuries, or even thousands of years, if we are talking about interstellar travel, and you begin to see how severe the problem becomes. Radiation does not usually kill you immediately. It accumulates gradually, causing mutations, destroying cells, increasing the risk of cancer, and eventually leading to the complete collapse of the biological system. And what is worrying is that when you travel at high speeds, especially at a significant fraction of the speed of light, these particles will collide with the ship with even greater energy due to relativistic effects, dramatically increasing the danger. You might think the simple solution is to build a shield thick enough to protect the crew, but you immediately return to the familiar problem: mass. To block high-energy radiation, you need very thick and very heavy materials, such as water, lead, or hydrogen-rich compounds. As soon as you start adding these protective layers, the mass of the ship increases rapidly, which in turn increases the energy demand, and the cycle we have seen before reappears. Even thick shields cannot completely block all types of radiation, especially the highest energy cosmic rays that can penetrate multiple layers of material and create secondary particles inside the ship, making the problem even more complex. Some ideas have been proposed, such as using artificial magnetic fields to simulate Earth's magnetic field, but generating a magnetic field strong and stable enough on a spacecraft is an extremely difficult technical challenge, not to mention the energy required to maintain it. This means there is no simple solution to completely eliminate radiation. It can only be reduced to some degree. And on a journey lasting centuries, even that reduction may not be enough to protect humans. When you combine all of this, you begin to see that radiation is not a secondary problem, but one of the central barriers to interstellar travel, because it attacks directly the most important thing you are trying to carry, life itself. And unlike collisions or energy, where you can imagine technical solutions even if they are difficult, radiation is a silent, constant, inescapable enemy. There is no way to completely remove it, making the interstellar environment not only physically dangerous, but also hostile to human biology itself. And even if you imagine that somehow we can reduce radiation to an acceptable level, there is still a deeper, more intimate, and much harder to solve problem, because it does not lie out there in space, but right inside our own bodies, biological limits. The human body is not designed to exist for long periods in a weightless environment. And this is not speculation. It is something we have observed directly from NASA missions over many decades. Astronauts who have lived on the International Space Station for extended periods have experienced bone density loss at a rate of about 1–2% per month, a number that is extremely alarming if you extend it over years, because it means your skeleton gradually becomes weaker, like an accelerated form of osteoporosis. It is not just bones. Muscles also atrophy because they no longer have to fight against gravity. And even with rigorous exercise regimens of several hours each day, astronauts still cannot completely prevent this decline. But the problem does not stop there. The cardiovascular system changes, bodily fluids redistribute, intracranial pressure increases, and even astronauts' vision can be affected after long periods in orbit, a condition doctors call SANS syndrome. More importantly, the immune system, the thing that protects you from illness, also weakens in the space environment, making the body more vulnerable to agents that might not be significant on Earth. Some studies even show that dormant viruses in the body can reactivate under microgravity conditions, and bacteria can become more aggressive, turning a closed ecosystem like a spacecraft into an environment with continuous biological risks. And all of this is only the result of missions lasting a few months to a year, under conditions that are still relatively close to Earth, where astronauts can be supported and brought back if necessary. Now imagine an interstellar journey lasting dozens, hundreds, or even thousands of years, where there is no possibility of returning, no rescue, and every biological problem must be solved on the spot in an environment that cannot fully recreate Earth's conditions. The average human lifespan today is about 70 to 80 years, and even the most optimistic scenario, you cannot complete such a trip within a single lifetime. This forces you to consider solutions such as extending lifespan, biological hibernation, or creating perfect life support systems across multiple generations. But the problem is that these technologies either do not yet exist or are only in the very early experimental stages. And even if they work in the short term, they have never been proven over centuries. Biological hibernation, for example, may work with some animal species, but applying it to humans for long periods without causing brain or bodily damage is still an unanswered question. Extending lifespan is not simple either, because aging is not a single mechanism, but a collection of complex biological processes that we still do not fully understand. And even if you could extend lifespan, you would still face the natural decline of the body over time, along with the cumulative effects of radiation, microgravity, and the closed environment. Some people propose creating artificial gravity by spinning the ship, but this requires an extremely large, stable structure that consumes enormous amounts of energy, and you immediately return to the technical and energy barriers we discussed earlier. In addition, a closed ecosystem must sustain itself not only physically, but also biologically, including food, microorganisms, oxygen and water cycles, and any small deviation in this system can lead to collapse over time. This means biology is not just a secondary factor in the interstellar travel equation, but a hard limit, because you cannot simply upgrade the human body the way you upgrade a machine. And when you combine all of these factors, you begin to see that the problem is not just getting a ship to the stars, but keeping the humans inside that ship alive, healthy, and functioning normally over a period far beyond any limits our biology has ever experienced. So even if you solve speed, energy, and radiation, you still have to face a simple but inescapable truth. The human body has limits, and those limits are not something you can negotiate or overcome by willpower. In the context of interstellar travel, they may be the greatest barrier of all, because in the end, you are not just trying to send a ship far away. You are trying to carry life across a distance that nature may never have intended to allow. A concept that emerged in the mid-20th century when pioneers like Robert H. Goddard and later researchers at NASA began to think seriously about interstellar travel. The idea sounds simple. If a single human cannot live long enough to complete the journey, then you do not need one human. You need many generations of humans, where the descendants of those who set out will be the ones who arrive at the destination. But as soon as you start thinking about it more carefully, you realize that you are no longer talking about a journey, but about creating an entire self-sustaining society floating in space for hundreds or thousands of years. If a journey to Alpha Centauri takes thousands of years at a feasible speed, that means dozens or even hundreds of generations of humans will be born, live and die without ever seeing Earth, without ever knowing the starting point of the journey, and possibly without fully understanding the destination. And this raises a very basic question. How do you maintain a stable, closed ecosystem over such a long period? On Earth, we have an entire biosphere with billions of species interacting in an extremely complex system that we still do not fully understand. And even with all our modern technology, we have never succeeded in recreating a completely closed ecosystem that can sustain itself long term. A famous example is the Biosphere 2 project in Arizona, where scientists tried to create a closed ecosystem with air, water, plants, and humans living together. And after only a short time, the system began to lose balance. Oxygen levels dropped, microorganisms grew out of control, and the project eventually required outside intervention to avoid complete failure. If a system built on Earth with the ability to receive constant support and intervention still encountered such difficulties, then maintaining a stable ecosystem in space with no support whatsoever over centuries is a challenge on an entirely different level. But the problem is not only biological and environmental, it is also social. A community living on a generation ship will develop its own culture, beliefs, and social structures over time. And there is no guarantee that later generations will continue to commit to the original goal of the journey. Imagine being born on a ship, never having seen Earth, never having seen the stars except through screens or small windows, and being told that you must live your entire life in a closed environment to complete a mission that your ancestors began hundreds of years earlier. You might start to ask why. What happens if a generation decides they no longer want to continue the journey, or they want to change course, or they simply no longer believe in the original goal? What happens if social conflict arises, political instability occurs, or accumulated management mistakes build up over time. In a closed environment, there is nowhere to go, no external resources. Any social collapse could lead to the collapse of the entire system. Even small issues such as resource distribution, power, education, or belief can become far more serious when amplified across many generations in a confined space. And you cannot reset such a society if it goes off course, because you cannot return to Earth and start over. This means a generation ship is not just a technical problem of building a ship large and durable enough, but a problem of maintaining a miniature civilization under extremely constrained conditions for a time far beyond any social system humans have ever sustained. And when you combine all of these factors, biology, environment, psychology, and society, you begin to see that the generation ship idea, however attractive in theory, actually opens up a whole new set of problems that may be even harder to solve than the ones it tries to avoid. So instead of simply being a solution to the limit of life, then the generation ship turns interstellar travel into a massive experiment in humanity's ability to sustain life and society under conditions that nature has never prepared us for. And there is no guarantee that the experiment will succeed. Humans did not evolve to live in confined, isolated spaces for years on end, let alone decades or centuries, because our entire evolutionary history took place in open environments, where there was always a sky, vast space, change, and diverse social interaction. When you place humans in a limited environment where everything repeats, every landscape looks the same, and there is no escape, you are putting them into conditions that their brains are not designed to handle long term. Even in relatively short missions on the International Space Station, where astronauts are there for only a few months, reports have shown significant levels of stress, insomnia, tension, and mood changes, even though they still have continuous communication with Earth and know they will return. Now remove all of that. No real-time communication, because interstellar distances mean signals take years to travel, no possibility of returning, no rescue, and nothing but the same repeating space day after day. In a journey lasting decades or centuries, this isolation does not just increase, it increases in a way that each generation will face a deeper version of it, because they are not only physically isolated, but also completely cut off from their history and origins. This creates enormous psychological pressure, where each individual must find ways to maintain meaning in an environment without natural change, without real day-night cycles, and without a clear sense of progress. And when you put many humans together in the same confined space for such a long time, conflict is no longer a possibility, but almost inevitable. Even in small communities on Earth, where there is open space and the ability to move around, social conflict still occurs. When you remove the ability to leave, remove surplus resources, and force people to live together under constant stress, you are creating an environment where any small disagreement can escalate into a crisis. In a closed system like a spacecraft, a major conflict is not just a social problem. It can become a survival issue, because it can disrupt management systems, resource distribution, and overall stability. And what is worrying is that there is no way to escape such a situation, because there is nowhere else to go. This makes every decision, every action, and every relationship far more important than on Earth. Some people propose that we could solve this by selecting the most psychologically stable individuals or training them to adapt to this environment. But even the best trained people have only been tested in missions lasting a few months or years, not centuries. The human brain has limits in handling prolonged isolation. And we have no experimental data showing that a community can maintain psychological stability under such conditions across multiple generations. And what is important is that the psychological factor does not operate independently. It interacts with all the other problems we have discussed. biology, radiation, environment, and society, creating a complex system where one problem can trigger or worsen the others. When you look at the whole picture, you begin to see that psychology is not a minor detail, but maybe the biggest weakness in the entire interstellar travel plan. Because in the end, no matter how good your ship is, or how advanced the technology, everything still depends on the humans inside. And if they cannot maintain psychological stability during the journey, the entire system will collapse from within, according to the theory of relativity developed by Albert Einstein in 1905. If time and space are not separated, but are linked together into a structure called space-time, and within that structure, the speed at which you move directly affects how you experience time. This may sound counterintuitive, but it has been proven experimentally. For example, atomic clocks on airplanes and satellites show that time really does pass differently depending on velocity and gravitational fields. When a ship travels faster, especially as it approaches the speed of light, time on that ship will slow down compared to time on Earth, an effect known as time dilation. This is not an illusion or a subjective feeling, but a real measurable difference. Imagine a ship that can reach a significant fraction of the speed of light, enough to complete an interstellar journey in a time frame the crew can live through. For example, about 10 years, according to the ship's clocks. For those on board, the journey would feel like a long but still lifetime scale trip. But when they return, they would discover that on Earth, not 10 years had passed, but possibly hundreds of years, depending on the speed they had achieved. The people they knew, their families, friends, and even the civilization they left behind might have changed completely or disappeared, and the world they returned to would no longer be the world they once belonged to. This turns interstellar travel into a form of one-way time travel, where you can move into the future but never return to your own past. And what is important is that you cannot avoid or turn off this effect, because it is not a technical problem that can be fixed, but a direct consequence of the way the universe is structured. Even if you use speed to lessen the time dilation effect, you return to the original problem that the journey becomes too long for humans to complete. This creates a paradox. If you go fast to shorten the subjective time of the trip, you become detached from Earth's timeline. If you go slow to stay synchronized in time, the trip lasts too long to be practical. There is no choice that allows you to travel far while still keeping a connection to your point of origin. And this is not just a personal problem, but a civilizational one, because any mission sent out would be unable to communicate effectively with Earth in real time. And whatever they discover would reach us as messages from a distant past. You combine this with all the barriers we have discussed: energy, collisions, radiation, biology, and psychology. You begin to see that interstellar travel is not just about crossing physical distance, but about accepting a complete separation from humanity's timeline. And that completely changes the meaning of the journey, because coming home is no longer a realistic possibility, but only a concept belonging to the past. When you leave, you do not just leave space. You leave your own time, and wherever you arrive is no longer in the same historical timeline from which you departed. This makes interstellar travel not only a technical or scientific challenge, but an existential one, because it forces you to face the question of whether a journey still has meaning if it separates you from everything that originally defined you. Putting all of that together, the speed of light, energy, collisions, radiation, biology, and even time, you might start to think that the problem is simply that we do not yet have good enough technology, that we just need to wait a few more decades or centuries, and everything will be solved. But when you look more closely at what we actually have, you will see a very large gap between imagination and reality. The propulsion systems we use today, from the Saturn V that took humans to the moon to the modern Falcon Heavy from SpaceX, are all based on the same basic principle, reaction thrust, created by burning chemical fuel. This works very well within the solar system, but it has a very clear limit, because the energy you can get from chemical reactions is extremely small compared to what is needed to reach interstellar speeds. The efficiency of chemical fuel is bound by the law of conservation of energy, and there is no way to make it stronger without completely changing the nature of that energy source. Even the most powerful rockets we have ever built can only reach speeds of a few dozen kilometers per second, while interstellar travel requires speeds of tens of thousands of kilometers per second. You might think we have more advanced technologies, such as ion engines, and it is true that such systems have higher efficiency in fuel usage, but they produce very small thrust and accelerate very slowly, making them completely unsuitable for reaching relativistic speeds in any reasonable time frame. Even more advanced proposals like nuclear thermal engines or nuclear rocket engines, although they have significant potential for improvement over chemical systems, still cannot bring us close to 1% of the speed of light, a threshold where, even if achieved, the journey to the nearest stars would still take hundreds of years. And what is important is that no current propulsion technology, whether chemical, electric, nuclear, or any variation of them, can realistically approach the speeds needed for interstellar travel. This is not because we have not tried hard enough, but because we are limited by very basic principles of physics concerning energy, mass, and momentum. Some people suggest that we may develop completely new technologies in the future, and that may be true to some degree. But even the most advanced ideas we have today must still obey the laws of physics that we understand. And those laws do not show a clear path to achieving interstellar speeds with propulsion systems we can build. When you look at the numbers, the gap becomes very clear. We are talking about moving from speeds of a few dozen kilometers per second to tens of thousands of kilometers per second. A difference that is not double or 10 times, but thousands of times. And each step up does not just require linear improvement. It requires leaps in energy and technology for which we see no signs that they can be achieved in the near future. So when people say, we just need better technology, they are overlooking an important reality. Not every gap can be filled by progress. And in the case of interstellar travel, the gap between our current capabilities and what is required is not only large, but may be one of the largest gaps humanity has ever faced. A gap that is not only technical, but concerns the very limits that physics imposes on any civilization in the universe. When you face the reality that all current propulsion technologies are insufficient, the natural reaction is to turn to bolder ideas, the kinds you often see in science fiction, where ships do not need to accelerate in the usual way, but bend space to get there faster. And that is exactly where the concept of warp drive comes in. In many movies and novels, warp drive allows a ship to cross enormous distances by contracting space in front and expanding space behind, instead of moving through space in the conventional way. And what is interesting is that this idea is not entirely imaginary, because the physicist Miguel Alcubierre proposed a mathematical model called the Alcubierre drive, which shows that, in theory, you can create a space-time bubble that moves faster than light without directly violating the laws of the theory of relativity. It sounds like the escape we have been looking for. But as soon as you dig a little deeper, you will see that this model requires something we do not even know exists. Negative energy. Not just a lot of energy, but a form of energy with negative density. Something that modern physics only allows to exist under very special conditions and has never been created or controlled on a large scale. Initial estimates even suggested that you would need an amount of negative energy equivalent to the mass of an entire planet to create a warp bubble large enough for a ship. And although later studies have reduced that number, it still lies far beyond any realistic capability. And even if you assume that one day we could create negative energy, there are still other problems, such as the stability of the warp bubble, how to control it, and what happens when you try to stop, all of which have no clear answers. Another idea often mentioned is the wormhole, or shortcut, where you do not travel through space, but go through a shortcut connecting two distant points in the universe. A concept that also comes from solutions to equations in relativity. Wormholes sound even more appealing than warp drive, because if they exist, they could allow you to travel almost instantly between 2 points. But the problem is that we have never observed a stable wormhole in nature, and theoretical models show that to keep a wormhole open, you again need the very exotic matter with negative energy we have already discussed. In addition, there are serious questions about stability, because even small disturbances could cause the wormhole to collapse before you could pass through. This means that both warp drive and wormholes, although very interesting theoretically, are based on assumptions for which we have no experimental evidence to confirm. And they require physical conditions far beyond what we can create or control. When you place them next to the barriers we have discussed, energy, collisions, radiation, biology, and time, you begin to see that they are not realistic solutions, but more like escapes on paper, existing in equations, but not in the world we can access. And what is important is that science is not based only on whether an idea can be written in mathematics, but also on whether it can be verified and implemented. Up to this point, warp drive and wormholes remain entirely within the realm of theory, and there are no signs that they can become practical technology in the near future. So when people say that we will find a way to exceed the speed of light, they are often relying on ideas like these, but if you look at the details, you will see that these ideas do not solve the problem. They only push it to another level, where the requirements are even more unrealistic. And that brings us back to the starting point. Perhaps the problem is not that we have not thought of the right solution, but that no solution exists within the framework of physics in which we live. Let's start with the simplest thing. You want to go faster to shorten the travel time, and to do that, you need more energy, because according to the principles we have discussed, acceleration always comes with increasingly large energy costs, but energy does not appear out of nowhere. You have to carry it in the form of fuel, and that means you need more fuel if you want to go faster or farther. Right at this point, the problem begins to twist on itself, because fuel has mass, and when you add more fuel to the ship, you are making the ship heavier. A heavier ship requires more energy to accelerate, and that brings you back to the starting point. You need more energy, which means more fuel, which means more mass. This is not a simple circle you can break with a small improvement, but an amplifying loop, where each step forward makes the next step more difficult in a nonlinear way. In rocket engineering, this is clearly shown in the Tsiolkovsky rocket equation, where the amount of fuel required increases exponentially as you want to reach higher speeds. And that means that to achieve the speeds necessary for interstellar travel, you do not just need a larger ship. You need a ship where most of its mass is fuel, and even that may still not be enough. You might think the solution is to use more efficient energy sources, such as nuclear or antimatter, but as we have seen, even those energy sources do not eliminate this loop, because they still must obey the laws of conservation of energy and momentum. And even if you reduce the mass of the ship to the minimum, you still cannot completely eliminate the need to carry energy, because there is no way to accelerate without consuming energy. This means you cannot design smarter to escape the problem, because the problem does not lie in the specific design, but in the basic structure of physics. And this loop does not exist in just one aspect. It spreads to every other aspect we have discussed. If you add armor to protect against collisions, you increase mass. If you add radiation shielding, you increase mass. If you add more complex life support systems to keep humans alive for a long period, you again increase mass. Every solution to one problem makes the other problems worse. And all of them come back to the same point: energy and mass. This creates a self-locking system where there is no single weak point you can exploit to break the entire loop. You can improve each part individually, but each improvement only moves you a small step forward, while the overall requirements increase even faster. When you look at this as a whole, you begin to see that interstellar travel is not a problem with a difficult solution, but a problem that may have no solution within the framework we are working in. And that is not because we lack imagination or technology, but because the laws of physics have linked these factors together in a way that makes any effort to overcome one limit lead you directly to another limit. This is the very nature of the impossible loop. There is no clear starting point to solve it, and there is no ending point where the problem disappears. Only a network of constraints from which you cannot escape. And when you understand this, you begin to realize that perhaps the problem is not that we have not found the right way to reach the stars, but that every path has been locked from the beginning. Looking at that entire loop, a very natural reaction is to say that humans have faced seemingly impossible challenges before and still overcome them, that perhaps interstellar travel is just the next step, just like the way we once left Earth and set foot on the moon. But this comparison, although appealing, hides a very important difference. The Apollo 11 moon landing was truly one of humanity's greatest achievements, a moment when technology, science, and human will came together to accomplish something that previously existed only in imagination. And when Neil Armstrong stepped onto the surface of the moon and said, "That's one small step for man, one giant leap for mankind," he represented not just one nation, but all of civilization. But what is important is to understand exactly what Apollo did and what it did not do. The distance from Earth to the moon is about 384,000 kilometers, a number that sounds large in the context of daily life. But on a cosmic scale, it is almost insignificant. Just a small step within the same planetary system, where we are still deep within the gravitational influence of Earth and the Sun, and where environmental conditions are still relatively familiar. The Apollo astronauts took about 3 days to reach the moon, and the entire mission lasted less than 2 weeks, a time frame that humans could plan, control, and manage risks for. Now place that number next to the distance to Alpha Centauri, the nearest star system to us, which is about 4.37 light years away, equivalent to about 41 trillion kilometers. That is roughly 100 million times the distance to the moon. This is not a difference of a little farther, but a difference in kind, where everything we understand about space travel within the solar system no longer applies directly. If you scale up the Apollo mission by 100 million times, you do not just need a bigger rocket. You need an entirely different system, an entirely different approach. And even then, you would still face all the barriers we have discussed: speed of light, energy, collisions, radiation, biology, and time. What is important is that Apollo operated within a physical framework where solutions existed. We could calculate orbits, supply energy, protect the astronauts, and bring them back within a finite time frame. No law of physics forbade going to the moon. It was just hard, very hard, but still within the realm of possibility. Interstellar travel is different because there you are not just facing difficulty, but facing limits that physics imposes, limits that cannot be overcome by technique or resources. When people say, "We once thought flying was impossible, then we did it. We once thought going to the moon was impossible, then we did it." They are implicitly assuming that all challenges are of the same type, that with enough time and technology, every limit will disappear. But what examples like Apollo really show is not that there are no limits, but that we succeeded when the goal lay within the range allowed by the laws of physics. And this is the key point. Interstellar travel may not lie within that range. The difference between going to the moon and going to another star is not a difference in degree of difficulty, but a difference between a problem that has a solution and a problem that may have no solution within the framework we are working in. And when you look at it this way, you begin to see that viewing interstellar travel as the next step in the space program is not only optimistic, but may be a misunderstanding of the very nature of the problem. Because the real next step may not be to go farther, but to understand more clearly the limits we are facing. One of the common assumptions when talking about civilizations beyond Earth is that they may be so far ahead of us that what we consider impossible becomes normal for them. But that assumption overlooks a basic point of science. The laws of physics do not change according to technological level or intelligence. They are universal. The speed of light is not slower in one place and faster in another. Energy is not easier to create just because a civilization is more advanced. And principles like conservation of energy or the structure of space-time are not optional rules you can find ways to avoid. What the theory of relativity describes does not apply only to humans. It applies to every object, every system, and every civilization in the universe, from tiny planets to enormous galaxies. This means that anyone, anywhere, if they want to travel between the stars, must face exactly the same barriers we are seeing: the speed of light limit, the enormous energy cost, the danger of collisions at high speeds, continuous radiation, and biological limits, or their equivalent if they are a form of life. There is no secret shortcut reserved only for a civilization that is smart enough, because these laws are not technology, but the foundation of reality itself. Even if a civilization could build technologies we cannot yet imagine, they would still have to work within the same physical framework. And that framework does not show a clear way to overcome the core limits we have discussed. This leads to a very thought-provoking possibility. Perhaps the reason we do not see other civilizations is not because they do not exist, but because they, like us, are limited by the same physical wall. They may explore their own planetary systems, and even build great structures in nearby space. But when they try to go farther, they encounter the same impossible loop. If that is true, then the universe is not silent because of a lack of life, but silent because no one can cross the distances between the stars in the way we imagine. This is exactly where the concept of the great filter becomes important. An idea in which there is one or more extremely difficult barriers in the development of intelligent life. And any civilization that cannot pass that barrier will never become an interstellar civilization. Usually, people think of the great filter as a biological disaster, nuclear war, or environmental collapse. But there is another possibility. The laws of physics themselves act as that filter, not by destroying civilizations, but by limiting the range they can expand. In this scenario, civilizations may exist everywhere, but all of them are trapped within their own star systems, unable to spread across the galaxy in the way we usually imagine. This also explains why we do not see clear signs of interstellar civilizations, because perhaps they do not exist, not due to a lack of intelligence or technology, but because the structure of the universe does not allow it. When you look at the problem this way, you begin to see that the question is no longer, why haven't we done it? But is it even possible at all? And if the answer is no, or nearly no, then that not only changes how we view the future of space travel, but also changes how we understand our place in the universe. Not as a civilization in the early stages of conquering the stars, but as a civilization that has reached a natural limit, a limit that perhaps every other civilization is also facing. This does not diminish the value of what we have achieved, but it places those achievements in a larger context, where progress is not infinite, and where the final boundaries are not set by us, but decided by the universe itself. One of the most understandable, but also most dangerous things in the way humans view the future is the belief that technology will ultimately solve every problem, that any limit we encounter today is simply temporary, and that with enough time, enough resources, and enough intelligence, we will overcome it. This belief does not arise out of nowhere. It is nurtured by our actual history, where many things once considered impossible have become normal. From flying through the sky to setting foot on the moon, from harnessing atomic energy to connecting the world through information networks. But that very history can also easily lead us into a form of illusion, that progress is infinite, that the curve of technological development will always continue upward without encountering hard boundaries. The problem is that when you look more closely at how science works, you will see that progress does not mean there are no limits. On the contrary, progress often comes with the discovery of deeper limits. What we have achieved in the past largely lies within the range that the laws of physics allow, and our success is not because we broke those laws, but because we learned to work more effectively within their framework. This is an important distinction because it means there are types of limits that technology can overcome, such as limitations in materials, design, or performance. But there are also limits that technology cannot overcome because they are not technical problems, but fundamental characteristics of the universe. When you say, we will find a way to go faster than light, you are not just talking about a technological improvement. You are implicitly assuming that laws like the theory of relativity can be overcome or modified at will. And that is a very large leap for which there is no supporting evidence. The same applies to energy. You cannot create energy out of nothing. You cannot consume less energy than physics requires for a given process. And you cannot avoid the consequences of mass and momentum. These are not challenges in the sense we usually use in engineering, where a clever solution can change the situation, but rather constraints that every solution must obey. When you do not clearly distinguish between these two types of limits, you easily fall into mixing up what is difficult, what is impossible, and that leads to unrealistic expectations about the future. Science fiction plays a large role in shaping our imagination, and that is not bad, because it helps us explore new ideas and ask important questions. But when those ideas are understood as certain predictions about the future rather than creative assumptions, they begin to create a distorted picture of what science actually allows. A warp ship, a stable wormhole, or a nearly infinite energy source may exist in a story, but that does not mean they can exist in the real world where we are trying to build technology. And this is the point where science needs to be clear. Science is not magic. It does not promise that everything can be achieved, but rather it tries to accurately describe what is possible and what is not within the framework of nature. In many cases, what science brings is not the ability to do more, but the understanding of what we can't do. And that is no less important. When you understand that some limits are absolute, you no longer waste resources and time on directions that have no chance of success, and you can focus on what is truly feasible. In the context of interstellar travel, this means that instead of assuming we will one day overcome every barrier, we need to seriously consider the possibility that some of those barriers are final. This is not pessimism, but realism, because only when you clearly understand the limits can you make the right decisions about the direction of development. And what is important is to distinguish between two questions. Is this difficult? And is this possible? History shows that we are very good at turning difficult things into reality, but that does not mean everything is only difficult. There are things that may lie outside the range of any civilization, not because they lack intelligence or resources, but because the universe does not allow it. When you accept that possibility, the way you view the future changes completely, not in a negative direction, but in a more accurate one. You begin to ask questions not only about what we can do, but also about what we should do, and what goals are meaningful in the context of those limits. Therefore, understanding progress correctly is not believing that every limit will disappear, but recognizing that real progress includes both discovering and accepting limits that cannot be overcome. And in the case of interstellar travel, that may be the first step toward understanding that the problem is not only that we are not advanced enough, but that we may be facing a boundary with no path across it. The key point begins to emerge when you no longer view each barrier as separate problems, but place all of them within the same framework and see them functioning as a single system, where each component is tightly linked to the others in a way that you cannot separate them. The speed of light sets a limit on velocity, and as soon as you try to approach that limit, the energy problem immediately appears, requiring enormous levels of energy that we would struggle to provide. When you increase energy, you have to carry fuel, and fuel increases mass, and mass in turn increases the energy demand, creating the loop we have already seen. But that loop does not exist in a vacuum. It spreads to other factors. To protect the ship from interstellar collisions, you need thicker armor, which again increases mass. To counter cosmic radiation, you need additional shielding material or magnetic field systems, which again require more energy and more complex structures. To sustain human life for long periods, you need more sophisticated biological support systems, which again increase the size, complexity, and mass of the ship. Every solution to one problem does not simply add a component, but triggers a chain of consequences that spreads throughout the entire system. This is what makes the problem especially difficult. There is no single weak point you can focus on solving to unlock the entire issue. In many engineering fields, you can find a main bottleneck, a factor that limits performance, and if you improve it, the whole system improves along with it. But in this case, there is no such bottleneck, because each limit is reinforced by the other limits. When you try to solve one part, you inadvertently make another part worse, and the system adjusts itself to keep you within the same range. This makes interstellar travel not a linear problem where you can progress step by step toward a solution, but a non-linear problem where the variables interact with each other in a way that amplifies complexity. You are not just designing a ship, you are trying to balance a network of mutually conflicting requirements. You need high speed, but cannot exceed the speed of light limit. You need large amounts of energy, but cannot carry enough fuel. You need protection, but cannot increase mass too much. You need to sustain life, but cannot guarantee biological and psychological stability over long periods. Each goal is reasonable on its own, but when combined, they create a system in which no configuration can satisfy all conditions at once. This is similar to trying to optimize a system with too many hard constraints, where no solution exists that satisfies all of them. And when you add the time factor, the problem becomes even more complex, because not only must the physical systems work, but they must work stably for decades, centuries, or longer, in an environment that allows no margin for error. A small error in one system can spread to others, and over time those small deviations can accumulate into the collapse of the entire system. In a closed environment, you have no ability to repair from outside, no additional resources, and no way to start over. This makes the complexity of the problem lie not only in the initial design, but also in ensuring the long-term stability of the entire system. When you look at the overall picture, you begin to see that interstellar travel is not a collection of separate problems that we can solve one by one, but a system where every problem is connected in a way that makes solving them simultaneously extremely difficult, if not impossible. And this leads to a conclusion that is not easy to accept. It is not that we lack a solution, but that there may not exist any single solution that can satisfy all the requirements at once within the current framework of physics. At that point, the problem is not just difficult, but becomes a problem whose very structure prevents us finding a solution. Everything that has been seen out up to this point begins to converge on a point that is no longer comfortable. Because when you try to follow any approach, faster, stronger, smarter, you always come back to the same result: deadlock. If you try to go faster, you run into the limit of the theory of relativity. If you try to increase energy, you are locked in the mass fuel loop. If you try to protect the ship, you make it heavier. If you try to sustain life, you have to carry an entire fragile ecosystem. If you try to bypass those constraints with ideas like warp or wormholes, you again rely on physical conditions we have never proven exist. Following any path leads you to a different version of the same problem. And that is not a coincidence, but a sign of a deeper limit hidden behind all those efforts. What makes this situation special is not that each individual barrier is too large, but the way they lock tightly together into a system with no escape, where every solution makes at least one other problem worse. You cannot optimize one variable without breaking another, and that turns the entire problem into a form of impossible balance. There is no simple solution waiting to be discovered, no single breakthrough that can make everything fall into place in our favor, because these barriers are not flaws in design, but characteristics of reality itself. This is completely different from the challenges humans have overcome before, where the answer existed but had not yet been found. Here, the real question is whether the answer even exists. And this is where the difference between not yet possible and impossible becomes important. Many things in history have moved from not yet possible to possible as technology advanced, but all of those lay within the range allowed by the laws of physics. In the case of interstellar travel, what we are facing may not be a technological gap, but a gap between our desires and what the universe allows. This does not mean we lack intelligence, creativity, or resources, but that we may simply be asking for something that the structure of space-time does not support. When you accept that possibility, the way you look at the entire problem changes. It is no longer a journey towards a distant goal, but a process of exploring the boundaries of reality itself. And at that boundary, every path stops, not because we have not gone far enough, but because there is no longer any path to continue. You can try to imagine the most ideal scenario, where all technology reaches its maximum level, every system works perfectly, and every risk is minimized. But even in that scenario, you still cannot eliminate the core limits. You still cannot exceed the speed of light. You still must supply energy corresponding to the speed you want to reach. You still must carry mass. And you still must face the interstellar environment. This means that even under the best conditions, the problem does not disappear. It only becomes clearer. And when a problem still exists, even in the most ideal scenario, that is usually a sign that the problem is fundamental, not something that can be solved by improvement. This leads to a difficult but consistent conclusion with all the evidence we have. Interstellar travel, in the way we imagine it, a ship carrying humans flying from one star to another in a reasonable time, may not only be very difficult, but nearly impossible. Not absolutely impossible in the philosophical sense, because science always leaves open the possibility that our understanding may change. But within the framework of everything we know today, every path leads to the same stopping point. And if that is true, then the idea of humans spreading throughout the galaxy may not be our future, but only a story we tell ourselves. This does not diminish the value of science or exploration, but it forces us to face a less romantic truth. Perhaps the universe is not designed to be conquered in the way we imagine. And in that context, the question is no longer, when will we reach the stars? But will it ever happen? And everything we have seen so far suggests that the answer may not be what we expect. Throughout history, humans have often defined themselves by their ability to overcome obstacles, by turning what seemed impossible into possible. And that very thing creates the feeling that there are no final limits, that every boundary is only temporary. But science, when taken far enough, does not only expand our capabilities, it also draws clear lines about what cannot be crossed. Understanding limits is not a sign of failure, but a core part of the scientific method, because science does not only answer the question, what can we do, but also answers the question, what can we not do? When Albert Einstein developed the theory of relativity, he not only opened a new understanding of space and time, but also set an absolute limit on speed, a limit that everything in the universe must obey. This does not diminish the value of physics. On the contrary, it makes our understanding more accurate and clearer. The problem is that psychologically, humans are uncomfortable with the idea of limits that cannot be overcome, because it contradicts the intuition that every problem has a solution if we try hard enough. This leads to a natural tendency to look for exceptions, escapes, or hypotheses that allow us to keep the belief that everything is still possible. But science does not work that way. Science is not built to comfort, nor is its purpose to maintain hope. It aims to describe reality as honestly as possible, regardless of whether the result matches our desires. Truth in science is not chosen because it is pleasant, but because it fits the evidence. And in the case of interstellar travel, the evidence we have is pointing in a very clear direction. There may exist limits that no civilization can overcome, not because they lack capability, but because the universe itself is structured that way. This places us in a different position from the way we usually view progress. Instead of asking, how will we overcome this limit? The question becomes, what do we learn from not being able to overcome it? Understanding an absolute limit is not the end of knowledge, but a deeper form of knowledge, because it allows us to clearly distinguish between what is feasible and what is not. When you know a door cannot be opened, you no longer waste time trying to open it, and you can focus on other doors. In the broader context, this also changes the way we view our place in the universe. Perhaps we are not a civilization on the path to spreading across the stars, but part of a larger system where every civilization is bound within its own range. That does not make us smaller. It only makes the picture clearer. And there is great value in seeing that picture accurately, because understanding reality correctly always has higher value than believing in a convenient version of it. In the end, if there is one thing science teaches us, it is that intellectual honesty is more important than comfort, and accepting that there are limits that cannot be overcome is not giving up ambition, but adjusting it to fit reality. In that sense, understanding limits is not a failure of science, but one of its greatest achievements, because it shows that we not only have the ability to imagine, but also the ability to recognize when that imagination goes beyond what the universe allows. Once we accept that there may exist physical limits we cannot overcome, the way we think about exploring the universe also needs to change, because exploration does not necessarily mean physically moving from one point to another. In reality, most of what we know about the universe today does not come from us going there in person, but from observing it from a distance with increasingly sophisticated tools. From Galileo Galilei's first telescopes in the early 17th century to modern observatories, humans have gradually expanded their view beyond Earth without leaving it. The clearest example in the current era is the James Webb Space Telescope, which has been launched, a tool capable of looking deeper into the universe than any telescope before it. Thanks to its extremely sensitive infrared sensors, JWST can observe galaxies that formed only a few 100 million years after the Big Bang, meaning we are seeing light that has traveled billions of years before reaching us. This means that when we look at those images, we are not only looking far into space, but also looking backward in time, observing the history of the universe in a way that no physical journey could achieve in the same time frame. And it is not just GWST telescopes like Hubble, radio observatories, and devices measuring the cosmic microwave background radiation have provided us with an enormous amount of information about the structure, evolution, and composition of the universe. We have discovered thousands of exoplanets, measured the mass of black holes, mapped the distribution of dark matter, and even inferred the existence of dark energy, all without leaving the vicinity of Earth. This shows that understanding does not necessarily have to come with physical presence. And in many cases, remote observation is even more effective because it allows us to access regions where traveling there is not feasible. When you place this in the context of interstellar travel, another possibility begins to emerge. Perhaps the way we explore the universe is not by going to the stars, but by bringing the stars to us through information. Instead of sending humans across distances that cannot be crossed, we develop tools that can collect data, analyze signals, and build models of what exists far away. With the development of artificial intelligence, sensors, and observation technology, this capability will continue to expand, allowing us to understand the universe more deeply without having to touch it. This does not diminish the value of exploration. It only changes the way we define it. Exploration is no longer about setting foot on a place, but about expanding the scope of our understanding, regardless of physical distance. And in a universe where distances may be impossible to cross, this approach is not a lesser substitute, but may be the only practical path. This also aligns with the nature of science, because science does not require us to be everywhere to understand everything. It requires us to build accurate models based on the data we can collect. And so far, that method has worked very well, allowing us to understand phenomena occurring at distances we cannot imagine reaching. Therefore, instead of viewing the inability to achieve interstellar travel as a failure, perhaps we should see it as a reminder that there are many ways to explore, and that a limit in one area does not necessarily limit all progress. In the bigger picture, science can still advance far, not by overcoming every physical barrier, but by finding other paths to understand the universe within the framework it allows. What really has value in this entire journey? In so many stories, the goal is always to go farther, to reach other worlds, to spread across the stars, as if the value of a civilization is measured by the distance it can cover. But if what we have seen is correct, if there are limits we cannot overcome, then defining value in that way may be wrong from the very beginning. Perhaps value does not lie in how far we can go, but in how much we can understand. What is most special about humans is not the ability to move through space, but the ability to build abstract models of reality, the ability to look at faint signals from the universe and turn them into structured knowledge. When Isaac Newton described the motion of the planets with simple laws, he did not need to leave Earth to understand the solar system. When Albert Einstein built the theory of relativity, he did not need to fly at the speed of light to understand how space-time works. This shows something very important. Physics is not only a tool for building technology, but a language that allows us to describe the universe accurately, whether we can get there or not. Through equations, observations, and models, we can understand phenomena occurring billions of light years away, places we may never set foot on. And that understanding is not inferior to physical presence, because it allows us to grasp the essence of what is happening, rather than just experiencing its surface. When you look at how science works, you see that every major advance does not necessarily come from going farther, but from understanding more deeply. Discovering the structure of the atom did not require us to go inside the atom in a physical sense, but required us to build models that fit the evidence. Understanding the evolution of the universe did not require us to travel backward in time, but required us to decode light that has traveled through space for billions of years. This leads to a different view of exploration. Exploration is not the act of moving, but the process of expanding the scope of understanding. In that context, the inability to achieve interstellar travel is not the end of exploration, but only a redirection of it. Instead of focusing on sending humans everywhere, we focus on bringing information from everywhere back to humans. And this in many ways is even more powerful because it allows us to access distances that physical travel could never achieve. When you accept this, you begin to see that the ability to understand is what makes humans special, not because it allows us to dominate the universe, but because it allows us to perceive our place within it. There is a big difference between touching a star and understanding how a star works. And in many cases, understanding brings far deeper value. This also changes the way we evaluate achievements. If the goal is to go as far as possible, then being unable to leave our own star system may seem like a failure. But if the goal is to understand as much as possible, then what we have achieved is extremely impressive. We have built a picture of the universe from the first seconds after the Big Bang to the large-scale structure of galaxies, all from a tiny planet orbiting an average star. That is not obvious, and it does not depend on how far we can travel. It depends on the ability to ask the right questions, collect data, and build theories that fit reality. And in that sense, understanding is itself a form of exploration not limited by physical distance. In the end, if there is one thing worth keeping from this entire story, it is the change in the way we define success. Success is not about whether we can conquer the universe, but whether we can understand it. And if the universe sets limits that cannot be overcome, then recognizing and understanding those limits is not a failure, but one of the greatest achievements a civilization can attain, because it shows that we not only have the ability to dream, but also the ability to look directly at reality and understand it as it truly is, whether humans can truly reach the stars, or whether it is all just a beautiful dream that physics does not allow to become reality. After all that has been analyzed, the speed of light, energy, collisions, radiation, biology, psychology, time, and even the limits of technology, the most honest answer is not yes or no. But we do not know for sure, but what we know at present does not support it. This is an important point, because science does not work by giving definitive answers when there is not enough evidence, but by building the best conclusions possible based on what we understand at the current time. And within that framework of understanding, interstellar travel, in the sense we usually imagine, a ship carrying humans flying from one solar system to another in a reasonable time, seems not only difficult, but possibly beyond realistic capability. But that does not mean the question is closed. Science is always open. Not in the sense that everything is possible, but in the sense that our understanding can always change when new evidence appears. What we consider a limit today may be understood better tomorrow, and in some rare cases, new understanding may open up possibilities we did not see before. However, it is important to distinguish between the possibility of changing understanding and the assumption that every limit will disappear. Intellectual honesty requires us to work with what we actually know, not with what we wish were true. This is especially important when talking about topics like interstellar travel, where imagination can easily outpace reality. There is a strong temptation to believe that if we are smart enough and persistent enough, we will find a way to overcome every barrier. But science does not guarantee that. It only guarantees that if a path exists, we may find it. And if it does not, we may recognize that. In this context, the real value of science lies not in always giving us the answers we want, but in giving us the correct answers, even when those answers are not easy to accept. When you return to the question of interstellar travel with this perspective, you begin to see that perhaps the issue is not that we need more time to achieve it, but that we need to understand more clearly what is feasible in this universe. And that does not diminish the importance of the dream. It only places it in a more realistic context. Perhaps we will never build ships that fly between the stars like in science fiction, but that does not mean we are limited in understanding the universe. On the contrary, as we have seen, the ability to understand can extend far beyond the ability to travel. Through observation, theory, and technology, we have been and are exploring regions of space that we may never set foot on, and we have built an increasingly clear picture of how the universe works. This leads to a conclusion that may not be as dramatic as conquering the stars, but is more profound. Perhaps the goal is not to reach the stars, but to understand them. And if that is true, then we have already come a very long way. This also returns to a core principle that science always emphasizes. Intellectual honesty is more important than comfort. Acknowledging that there may exist limits that cannot be overcome is not giving up ambition, but adjusting it to fit reality. And in many cases, that very adjustment opens up new directions we did not see before. When you no longer try to break through an unbreakable wall, you begin to look for other paths around it, other ways to achieve the goal of understanding. In the end, the story of interstellar travel is not only a story about technology or physics, but a story about how we face limits. And in that story, what is remarkable is not whether we can reach the stars, but that we can ask that question, analyze it, and arrive at an honest answer based on evidence. Perhaps we will never step onto a planet orbiting another star, but we can understand the light from that star, its structure, its history, and its role in the larger picture of the universe. And in many ways, that is already a form of reaching there in a deeper sense. So when we return to the original question, the answer is not a closed conclusion, but an open realization. Interstellar travel may be nearly impossible within the current framework of physics, but the ability to understand the universe is not. And it is that ability that truly defines us. If you want to explore deeper into the limits of the universe and the big questions that science is facing, please subscribe to the channel so you don't miss the next analyses. See you in the next video, where we will continue to go farther, not by distance, but by understanding.